let's take a look at some properties of continuity. And let's start off with a theorem. If b is a real number and f and g are continuous at x equals c, then the following functions are also continuous. The first one is referred to as a scalar multiple. B times f is continuous. So as an example, if f of x equals x squared, we know it's a polynomial that's continuous everywhere. So if b is a real number and I multiply a real number by f of x, that's also continuous. So let's let, as an example only, b be equal to, 3. That would give us 3 times f of x, which is 3x squared. This is also continuous. Now, sums and differences are continuous. So if f is continuous, and g is continuous, then f plus or minus g will also be continuous, specifically at this point x equals c. Which makes sense if you think of a quick example. Let's let f of x equal, again, how about x squared? And that's clearly, it's continuous everywhere. And g of x equals, x. Then f of x times g of x equals x squared times x, which is x cubed. That's also continuous everywhere. Now, this didn't work simply because I picked functions that are continuous everywhere. I could have done the exact same thing with sine and cosine. So if I take this example, let c equal pi over 4, well, sine of pi over 4 is in fact defined as root 2 over 2. Cosine is defined at pi over 4. There's no discontinuities anywhere there. So that cosine of x is actually, of pi over 4 is also root 2 over 2. So if I multiply these together, I'm still going to get a function, this function, which is continuous at c equals pi over 4. If I were to change this sign to say tangent, tangent has a bunch of discontinuities. But tangent is defined at pi over 4, and it's defined about an open interval of pi over 4. So tangent x times cosine x is also continuous at pi over 4. And actually, you can quickly see what it is. This is the same as saying sine x over cosine of x. That's tangent times cosine of x. That's just sine of x. So the products, if two functions are continuous at a specific point, then the products are also continuous. Same thing is true for the quotient, but the quotient you have to be a little bit careful of because g of c can be non-zero. As an example, let's just say f of x equals sine of x. G of x equals cosine of x. Well, if I say, if I take a look at h of x, which is equal to f over g, which is sine of x over cosine of x. Sine's continuous everywhere. Cosine's continuous everywhere. However, cosine can be 0. And when cosine is 0, by the way, sine is not 0. So this ends up giving me vertical asymptotes. And in reality, this is, as I said a few moments ago, just tangent of x. So as long as cosine of x is not 0, that's what my g of x is using this notation right here. Then if sine of x and cosine of x are continuous at c, then tangent is continuous at c. Now I don't have to stick with sine and cosine giving me tangent. Let's just do another quick one here. How about f of x equals 3x squared? And now I'm going to toss in a trig function, g of x equals sine x. Well, that would then imply, as in all this, that 3x squared over sine x, 3x squared is a polynomial, is continuous everywhere. Sine x is continuous everywhere. That implies that this ratio would be continuous everywhere, except this is continuous for all x that's not equal to n pi, for n being in the counting numbers. And an element of the set 0, 1, 2, and so forth. because sine is 0 at 0, pi, 2 pi, 3 pi, and so forth. And that's what this is saying. We're just simply putting a restriction for when sine is not 0, because this is what makes it 0. So this ratio would in fact be continuous everywhere except when sine of x is equal to 0.